Okay, so this week we're going to focus on the hazards associated with earthquakes. So last week we were kind of just doing the nuts and bolts about magnitude and location and why we have ground shaking and things like that. So this week we're going to focus just on the hazards, a little bit of prediction and prevention also. So let's see what we got going on here. So one of the things that I want you to be aware of is that there are a lot of factors that impact the amount of damage that occurs. So certainly the size of the earthquake is important, and usually the larger the magnitude, the more energy that's released. So obviously that has an impact on the amount of damage. But you can see from the factors that I've listed here, there are other things that are going to control that. So obviously if you're far away, so distance. So remember, the focus is something that occurs inside the earth. The epicenter is on the surface. So distance from either of those is going to help you. The farther away you are, the less damage. That's kind of common sense, I think. And of course the size, we talked about that already. But some other things you might not think about is how long does the earthquake last? And so an earthquake that shakes the ground for minutes do more damage than something that shakes the ground for seconds. And certainly what the material that you build your structures on, right? That's going to come into play. How many people are there? How you build your buildings. And so one of the things you'll hear commonly when we talk about damage or death that occurs during an earthquake is that earthquakes don't kill people, buildings kill people. Because let's face it, if you were in the middle of an open field and an earthquake occurred, even if it was severe and it was right near you, you might fall over because the ground is shaking so hard. You're not going to have, the earth's not going to open up and you're going to fall into a crevice like in the movies or something like that. You would survive that because there's nothing really to hurt you except, you falling onto the ground potentially. But usually what happens is buildings collapse, and of course people are in those buildings, or freeways collapse and people are on those freeways. This is where a lot of the deaths occur, is from the collapsing of buildings and things like that. So I want to keep that in mind when we're talking about damages. But when we talk about things that occur from earthquakes, certainly the ground can rupture. It doesn't always make it to the surface, of course, but on occasion we see the fault plane actually coming to the surface and being exposed. Now obviously if your home or structure was built across this and the ground elevated or dropped, that's going to have some impact on how well your structure will survive the event. But it's pretty rare to be right on that. The ground shaking, of course, is going to occur pretty far from this epicenter here. But certainly ground ruptures can break pipes, break water mains, break gas lines, things like that. And we know that that can lead to some problems for sure. But ground rupture is one thing that we would want to take a look at. And it depends on, what the ground looks like. And so in some cases it can just crack here, so we don't see a lot of movement. But that could mean that there's a lot of soil here and the movement is at depth and not exposed at the surface. Sometimes we get vertical motion. And of course we do get horizontal motion. So remember, we said that we're identifying the different types of earthquakes based on their motion. So a horizontal motion would indicate a strike slip or shearing motion here. Vertical would be some type of dip slip, either reverse or normal. And so we see these ground ruptures that once again can have impact on structures if they happen to be over top of them. Another thing that we see doesn't happen everywhere, but we notice that where two plates collide, collisions, subductions in particular, usually happens near coastal communities. And so this is a place like, let's say, the Andes Mountains, right? So on the west coast of South America, we have subduction. There's beaches there. So where we are close to sea level, there is water in the subsurface, right? Groundwater. And so when we have water that is near the surface and we shake the ground, a lot of times we get a rising of the water toward the surface. And so temporarily it turns the solid ground into a liquid. And once again, if your structure is on that and it becomes unstable, we get motion and then the foundations crack or the buildings fall or things like that. So what we need for liquefaction to occur is we need water that's in the subsurface, and we need it to be near the surface. Because what's happening here is water is being stored in the ground in sediment, typically, so pieces, right? In this case, not turned into a sandstone yet, just sand pieces. But water can percolate down into the subsurface and fill up these spaces. When I shake it, these things bounce into each other and basically push the water upward, and that causes the material above to act like mud or like quicksand almost, and it can be fluidized temporarily. And so here in Arizona, our water table is too low. Even if we had big earthquakes, we wouldn't really see this phenomenon because it's not near the surface. But in coastal communities, we typically see that. So liquefaction is a problem there. And so in some examples here, we see that this is a building. This is the top of the door. So the door is down here. And so this building actually sunk into the ground when the earthquake occurred. Or in some cases like this, where it looks like the ground actually flows temporarily, almost like a mud flow. And so, of course, if your home is on that, you're going with it. Other cases where we had buildings just topple over. So they didn't collapse because they were structurally unsound. But what they were built on became liquefied during the earthquake, and it caused the building to become unstable, tip over, things like that. Another effect we want to talk about, and we're going to talk in the next module specifically about tsunamis, but we know that under certain conditions we can get a tsunami that is generated. Typically, tsunamis are generated because there is an earthquake that occurs under the ocean floor, under the sea floor, and there's some type of displacement. So motion up and down, and so what that does is uplift a water column and causes a large wave to be generated, which moves away from where the earthquake occurred or the uplift occurred. And so then we see this wave generating and moving away from the source toward land typically. And so once again, this is typically happening near subduction zones where the contact between the ocean plate and the continental plate is actually out in the ocean. And so when there's slippage along that plate, we see vertical motion occurring under the ocean basin, and that lifts up seawater, and of course that can move in all directions, be super fast. And so the problem that we see with tsunamis, and like I said, we'll talk more about this when we get into specifics of tsunamis in the next module, is that when there's motion under the ocean here, we get this uplift, we get a really big wave, and these waves move extremely quickly, but out in the deep ocean, they're fast, but they're not very tall. But what happens as they move closer to the coastline and the seabed here gets closer and it shallows up, we get these very large waves that grow super tall. And so we have fast moving waves that are really tall, and of course they can cause lots of damage. And so as they get close to the coastline, they might be, maybe 5-10 feet out in deep ocean, but when they get really close to the coastline, they can be 50, 60, even 100 feet tall, and you can imagine that that can cause lots of damage for sure. And so some examples we might see of that, we have this impact here where a wave struck the coastline and sheared off trees here. Obviously, if there's homes in the way, and we have certainly some examples of that too. So relatively recently, 2004, 2011, these were very large earthquakes, both at subduction zones. Both generated a huge tsunami, and so the damage here was done not only by the ground shaking from the earthquake, but this secondary kind of hazard that was generated, the tsunami, and then that wave moved in and caused extreme damage there. So another effect that we have to be aware of. And then landslides, once again, we're shaking the ground, so depending on the conditions of where you live, you can get large landslides that occur. So is that the common everywhere? Well, not if it's relatively flat. So if you don't have steep slopes or unstable slopes, then you're not going to get these types of effects. But certainly when we have collisions of plates, we tend to get mountainous regions, so they're relatively steep. And so when we have this collision and ground shaking, we tend to get landslides that occur, in some cases more than others. And an example of that would be in 2015. There is a large earthquake in Nepal. This is a collision between two continental plates. So there's no subduction here, but there's large mountain building that occurs here. So a very steep mountainous area. And so there was lots of landslides that occurred here. No tsunami, we're not near water. So in this case, the big and a side effect of the earthquake was landslides. Of course, fires, so fires can be a problem. We talked about that the movement of the ground can shear water mains and gas lines. And so the gas lines rupture, you get a spark, and boom, you get a fire. Water mains break, and then you can't put out the fire. So a lot of times after earthquakes, you get fires that potentially could be uncontrollable. There's also some effect that we see on how the ground moves depending on the type of material that exists. And so what we typically see is the term bedrock that we're going to use here is any solid rock. So igneous, metamorphic, sedimentary. These are what we're going to call bedrock. And then the other types of materials are sediment. And so sands and gravels as sediment or mud as sediment. And typically what we see is the muds are the worst. And so they actually amplify the shaking because, of course, they're small pieces that can bounce together, whereas the bedrock is cohesive and we don't see as much ground shaking. So in areas, once again, near coastlines where you have lots of sediment deposited, the areas made of mud are typically where we see the most damage because it shakes the most as the waves move through it, where the bedrock is very stable and doesn't shake as much. And so just another example of that. And in some cases we get some really weird shaking because the height of the building, it sways, and it's very similar to the amplitude of the seismic waves that are moving through, so you can get some really weird stuff that occurs there. An example of where we have this amplification of the material is in Mexico City. So Mexico City is actually built on a big mud flat. It's an ancient lake. And so lake deposits are usually muds. And so when they built Mexico City, it actually used to be near a lake, and they drained all the water, and now they have a beautiful little mud that they built all their homes on. So when earthquakes happen here, damage tends to be more severe because most of the structures are built on muds, which amplify the wave energy. All right. You can kind of read through those a little bit. So how do we prevent? Well, we don't prevent, right? But we can try to reduce the amount of damage that occurs for our earthquakes. And typically what we can do for that is we generate some type of map that indicates the hazard. So geologic maps that indicate earthquake hazards. So we said that material plays a role here, so identifying the rocks and materials that exist on the surface, making geologic maps, can indicate where the greatest hazards are. Like places where we identify lots of muds, we might say, hey, this is a liquefaction area, a place where that is common, and so you want to be aware of that during an earthquake. Other places where we have bedrock, we don't have that hazard. So by identifying the type of material at the surface, we can help with high risk zones. So it can be, of course, local, where we make little local maps. It can be kind of larger, where we look at the whole continental U.S. and say, hey, your chances of an earthquake are pretty high over here. Why? Well, we have high stress, a collision here. Whereas other places where there's no stress or low stress, we don't have high risk. So we certainly want to put together these maps that indicate where the highest risk is so we can prepare. We also want to educate. So that's common for all of kind of these geologic hazards we see. We want to tell people what to do in an earthquake. And of course, with the maps, we want to tell them where they're at the most risk. We also want to build buildings that can withstand the ground shaking and the energy that's released here. So now that we know where there are high risk zones, what do we do about it? Well, let's build buildings that can withstand some of these huge events. And so one of the things that was discovered after some unfortunate earthquakes was that you can't really have parking garages and open spaces below buildings because it's weaker and they tend to collapse. And so those were kind of not built anymore after that. So these are the things that would affect how we would build our buildings. And so how tall and the weight distribution, what we're building it of, and how it's attached to the ground, all these things we want to take into consideration when we build earthquake-proof or earthquake-resistant buildings. Some other things that we take into account when we're building buildings, you can look through those. And then, can we predict earthquakes? Well, we really can't. And I don't know that there'll ever be a time where we will be able to predict earthquakes. But there are some things that we can kind of pick up on that might give us an indication. So there's some short terms and long terms. Now look, sometimes we get small earthquakes before a large earthquake. So we get a 5.2, and then a couple minutes later there's a 5.8, and then an hour later there's a 7.2. So those first two were considered foreshocks before we had the large earthquake. The problem with that, of course, is you could just get a 5.2 and nothing else. So you don't really know it's a foreshock until you get the big one. But if you get a small earthquake, you should be prepared that there could be a larger earthquake coming. So there is a little bit of prediction there. This one I threw in there just for fun, but it's not really a scientific predictor. But there has been lots of anecdotal stories about dogs barking or horses running out of barns or birds flying and all that kind of stuff. So potentially, pre-uplift. So sometimes the ground surface actually rises up, but this would have to be something that we're monitoring at the time that the earthquake is going to occur. So obviously that doesn't happen everywhere, and we don't have the technology to monitor everywhere. But if we are monitoring some of the ground surface and we see an increase in uplift or a change, could be an indication that there's going to be a rupture soon. Wells, water drops in wells, because as the earth kind of cracks a little bit prior to rupturing everywhere, we get more porosity and water can move through. Same thing with radon gas increases. The cracking can cause radon gas to be released. Longer term predictions, we look at a couple things, and usually we're doing averages. So either it's a record that's been written down that we say, hey, there was an earthquake in 1902, and then an earthquake in 1950, and then an earthquake in 2000. They're roughly 50 years apart, so on average you get an earthquake every 50 years. So we're kind of looking at an average to figure out when's the next one going to come. Sometimes we use what's called a gap, where there has been no earthquakes in an area where we know there's a big stress buildup. And so the longer there is not an earthquake there, the higher the risk and the larger the earthquake potentially could be. We also sometimes find areas where there's been offset an earthquake, and we can go in and dig a trench through that fault and estimate how many times it's moved under certain conditions. Of course, we need some datable material to give me some times between the earthquakes, and then I can just take an average. If I'm measuring slip rate, which means, or I'm measuring stress, which once again means I have to have devices at that area that are constantly measuring that. I can use GPS to see that plates are moving. And so if I see an increase in movement, maybe that means increase in stress. So I could say maybe an earthquake is happening sooner than later. The idea of the seismic gap story is kind of counterintuitive, but sometimes what happens is whenever there's an earthquake, it releases stress along a fault. And so where we have a place where there has not been an earthquake, we argue that stress hasn't been released. So let's say this is a long fault system here, and I've had earthquakes here. So this is stress, so the purple is low stress. So earthquakes have released stress here, and here, and here. But right here in the middle, there hasn't been an earthquake recently, which means the stress hasn't been released. So although these places have had earthquakes recently, you might think, oh, they've had an earthquake recently. They're probably an earthquake-prone area. They're going to have another one soon. But we'd actually think that there probably won't be one for a while because the earthquake released the stress there. Where here, where there hasn't been an earthquake in a while, the stress is still high. So we would argue those areas where the gap in seismicity is would be at a higher risk. So we can use that information. And then finally, talk just a little bit about this. So this isn't really a prediction method, but it's a piece of equipment, I guess, an early warning system called Shake Alert that's actually been used in Japan for years and is just recently becoming online in California. But it doesn't predict an earthquake, but it tries to warn people that ground shaking is occurring. And that is because we know something about how P and S waves move. When there's an earthquake, we said the P wave is super fast. It hits my sensor before the S wave, and as a general rule, the S waves do much more damage in ground shaking than the P waves. And so there's a lag here. So once it hits my sensor, it can run to my little processing center and send out an alert to people's phones that say, hey, here comes an earthquake and the S wave's going to hit you in 15 seconds or a minute. So it's not the greatest of warning systems because it doesn't give you a huge lead time to when the ground shaking is going to occur. But it might be enough to get under cover because we said, look, if you're trapped in a building, we know falling objects could hurt you. You can get under a desk. Maybe you can get out of a building in time depending on the amount of lead time you have. So that's an interesting technology. And of course, it works at a sweet spot. So if you're super close, like let's say the epicenter is right here, well, obviously the lag time is too short. We can't warn people. And of course, if you're really far away, the ground shaking isn't a problem because the energy dissipates. So there's kind of this sweet spot where when there's an earthquake and you're a certain distance away, you can get a short warning that can give you an advantage and maybe protect you. So that's what kind of the Shake Alert system is. So you can run through the slides, and of course there's a bunch of links here that talk about the different earthquake types and some of the other hazards. So you want to take a look at those too. All right.